Hi everyone, let's start part 3 of chapter 2. In this part, we will have a multi-server modeling for a queuing system. In the first two parts, part 1 and part 2, we had a Monte Carlo simulation, also a single server queuing system, right? So in this part, we are going to have a multi-server queuing system. So somehow we are extending that single server to a multi-server to be more complex. So let's see how we model a system with two servers, okay? So here we have an example, and we call this as Able Baker Call Center. So here we assume that we have a computer technical support center, and we have two staffs there, Able and Baker, okay? And the interval times for the calls is distributed by this distribution. So the interval time between the calls could be between 1 and 4 minutes. And as you see here, we have the probabilities. For example, with 25% chance, the interval time could be 1 minute. With the 40% chance, it could be 2 minutes, or let's say, for example, with 15% chance, it could be 4 minutes, right? And so this is the PMT, probability mass function, and here we have the CDF, cumulative probabilities. So here we just add up the probabilities in order to have in cumulative order. So for 2 minutes, it could be 0.25 plus 0.40, so it will be 0.65, right? And so on, okay? So this is the inter-arrival time distribution for the calls. For the Able and Baker, we assume here that Able is more experienced than Baker. So because of that, the service that Able provides is faster than Baker. So this is why here we see that the service time for Able varies between 2 to 5 minutes, but the service time for Baker varies between 3 to 6 minutes. Okay, so Able is 1 minute faster than Baker. Okay, and the same as IAT, interval time. Here we have the probabilities and also the CDF. Okay, so we calculate the CDF for the service times of Able and Baker. Okay, and here we have a rule. So this is our discipline for this system, that when both are idle, Able takes the call. So when we have a call and both Able and Baker are available, then in that case, Able will take that call. So this is our discipline, right? Because the Able is more experienced, and the service that he provides is faster than Baker. So here we assume that this is our discipline, right? We set that rule that anytime that both are available, Able will take the call, okay? And if both are busy, customer waits in queue. Yes, when both servers, same as a single server. When the servers are busy, then the customer or the call will join a line, okay? So here is the purpose of our simulation. We want to estimate the caller delay or hold time or waiting time. Okay, so yeah, we would like to estimate the waiting time for the calls. In average waiting time for the calls when any of the servers, Able or Baker, will answer the calls. Okay, so and we want to estimate this average by running the simulation model for 100 calls. Okay, so this is our problem definition here. Okay, so in order to model this system, at first we need to define the notations, right? So the interval time for ith customer is defined by AI. Okay, and so the arrival time of the ith customer would be this. We had this in single server, right? And the required service time for ith customer, we showed this by SI, and the able's earliest available time to answer the call for ith customer is a API. So yeah, since here we track the system by customers, I mean, we track each customer one by one. So for any customer, we will have a variable. We show this by ABI, and that will be the earliest available time for able in order to take the ith call. Okay, and same as this, we have a variable for Baker. Now, yeah, and then based on the availabilities, we assign a staff, we assign a server to answer the ith customer, and we show this by SFI. Okay, staff assign. It could be Able or Baker, and the service start time of ith customer, we show this by SSI, and the Able, yeah, again, the service end time for a customer for a call, it depends to the server, right? So if the Able is the server of that call, then we show this but SET ABI. I mean, service end time if Able is the server of the ith customer, and SET BKI, so service end time if the Baker is the server. Okay. And the waiting time, we show the waiting time of ith customer by WI. Okay, and in the maximum we have n calls. Here we have 100 calls. So this is our notation for modeling this system. And here is the general flow of the simulation of this model. So we call this is a flow chart, and by this flow chart we are showing that how in general the simulation model will work. So at first we initialize the simulation parameters, and then we have the call arrival. So when a call arrives, at first we check if Able, since we assume that in case of both servers are available, Able will take the call. So at first we check the availability of the Baker. If the Baker is available, we go to this branch, and so that call it sees Able, and then after having the service release the Able and leaves the system, right? If the Able is not available, we check the availability of the Baker, and again, if it's available, then it goes to the same process. But if the Baker is not available, that call will join a line queue, right, in a waiting line. Okay, and at the end, we will compute the statistics, and we will terminate the simulation if we have simulated for 100 calls. If it's less than 100 calls, then we will repeat all the process from call arrivals to this step. Okay, and that's it. If we have 100 customers in the system, then we are done, and we print the statistics and we terminate the simulation. Okay, so this is the general flow of the simulation of this system. Okay. So after having the general flow chart and also the defined notations, we need to show somehow the pseudocode of the system. Here we will have more details than the flow chart that we had in general form. Okay, so let's see what are the details here. So at first we set the n as 100 and I as 1. So this is the initialization in our simulation. And we generate interval time of ith call. Here, for the first step, I is 1. So here, actually, we are generating the interval time for the first call, right? And we calculate again the interval time of the ith call. Now here is the point that we check the availability of the Able, right? So as you remember, we had the ABI as the earliest available time for Able, right? So here we check if the arrival time of the ith call is greater than or equal to ABI, then we will assign Able to this call. Okay, so by this SFI will be Able. Else, we check the availability of the baker. So we check if AI, the arrival time of ice customer, is greater than or equal to BKI. Then again, if it's true, then we'll assign baker to this call. So SFI becomes a baker, right? Or else, both are not available, then we will calculate the earliest available server. So we will take the minimum between ABI and BKI, and then here how we assign a server to this call. If the minimum of ABI and BKI is able, then the server for that call will be able, or else it will be baker. Okay. And here we calculate the service time of auth caller. Yes, here since we know that actually who is going to be the server of this call, then we can calculate the service time, because the service time depends to the server, right? So here we calculate this, and we will have the SI, and then we can calculate the service start time of auth customer. We show this by SSI. So SSI will be this. If the SF, the server for this call is able, then the maximum between AI and ABI will be the service start time for this call. Other than that, if the baker is the server, then the maximum between AI and BKI will be the service start time for this call. Okay. Now we can calculate the service end time by having the service start time and the service time that we have calculated in the previous step. So we can calculate the service end time. Okay. So yeah, for able and baker, it's different. So here we just need to add the service time to the service start time for both, right? And it depends who's the server. Okay. And then we calculate the next earliest available time for able and baker. So as you see here, for the next call, AI plus 1, the earliest available time for able will be this. If for I, the server is able, then SSI plus SI will be the earliest available time. Else, it will be ABI. Okay. And with the same manner, we calculate for the baker, and then we compute the call waiting time and other statistics. And so yeah, waiting time will be the service start time minus the arrival time. And yeah, we check if we have simulated for n customers here for 100 calls we stop. Other than that, we repeat the steps from generating the interval time. Okay. And this is how actually this simulation model works in detail. And after running the simulation model, we need to calculate the performance measures. So here, these are the measures that we define for the system. For customers and servers, for customers, probability of customer to wait, yeah, number of customers wait divided by the total number of customers, average interval time, average service time, average waiting time. These are all exactly the same as before. There's no difference between these measures in multiple server or single server. Okay, average sojourn time and average waiting time for those who wait. Yeah, exactly the same as before. And for the server, again, these are exactly the same as before, but just here we have more servers than one server, right? So we calculate the able idle time, we calculate the able utilization rate, we calculate the able idle time and baker idle time and baker utilization rate. Yeah, the formula is exactly the same as before, but here we need to calculate these measures specifically for each server. Okay, so we'll see how we calculate all these measures and also how we implement the simulation pseudocode, the process of the simulation in Excel in the next part. Okay, so thank you.